So let us now look at the timing analysis of the R type instruction. Okay, we are specifically looking at the instruction x1, x2, x3, right? So basically what we want to do is to add x2 and x3 and put it into x1, right? So in order to do this, we are going to make use of this block diagram that we had constructed, right? So ignore this blue line, that is nothing significant about this. It is just the I needed a block diagram without any annotations, and this was the simplest that I could find. Okay, so as we discussed, right, the launch flop for any instruction is basically the program counter, right? So essentially what is going to happen is the clock is going to pulse, and then the PC next is ready and it has been latched by that particular flip-flop, right, out here, and essentially I shall mark the delays here. So this is TPCQ of my program counter, okay, propagation clock to queue delay, right? And it has basically obtained the address of the next instruction, right? So that is what is going to be available at this point. I'll use a different color for that. So this is going to be the address, and that is connected to the address port of the instruction memory. And remember that the instruction memory is essentially a combinational block, and therefore data is going to be read out of that memory after a delay of tmem, right? It's going to take tmem for it to appear at the instruction at the data port of the instruction memory, and therefore here you are going to get the instruction which corresponds to this add x1 comma x2 comma x3, right? Just to remind you, the format is add destination register rs1 rs2, right? So effectively what is going to happen is on bits rs1 is going to be my a connected to a1 register, right? So this will basically be 2 because rs1 is 2, right? And a2 is going to be my source register 2, which is 3 x3, right? And my destination register is the x1 register, right? And therefore this will be 1. Okay, now what has happened is the instruction has come in and now has simply branched out into 2 different blocks in parallel. Okay, so therefore the control unit is now going to start decoding this instruction, but at the same time the register file is also going to start decoding the registers. Now this is a good point to highlight the nice instruction structure of the RISC V processor, right? It's not that, for example, you had to go through the decoder and then figure out, okay, you know what the registers are and so on. The register address is available directly, you just feed it straight away into this register file and then you get it, right? Otherwise what will happen is you have to go through a decoder, then get the register address and then feed it to the register file. That is extra time. Okay, so now what's going to happen is your address bits OP0 to 6 is going to be decoded. You will figure out it's an R type of instruction, and the control unit is basically going to take T decode. Okay, after a time of T decode, this all the control signals of at the output of this control unit are guaranteed to have stabilized to their final value, right? So therefore if you look at it, for example we would have enabled write enable here, right? Because we are ultimately writing back to a register, so this is going to be 1, right? then your IMM source would basically be 0 because you are actually going to choose from the register, right? So therefore, that will be 0. I will not highlight it. ALU source, actually IMM source does not matter. I'm sorry, it does not even matter what the value is, because you are going to completely bypass it and your ALU source is going to be 0. Why? Because you are going to perform two operations on registers. Okay, so now what we are interested in is, of course, memwrite is 0, ALU control is going to be set accordingly to the add operation, which happens to be 0 in this case, right? So all of this is nicely set here, and these signals are set correctly after a time of T decode from the time the instruction is available to the control unit and the register file in parallel. Okay, so now what's going to happen, you're going to take a time of T RF read to read the data, right, to take this address of the two registers, right, A1 and A2, okay, which happens to be 2 and 3 respectively in this case, decode the address, turn on the tri-state inverter, and that is the RF read time. So therefore, the data sitting in X2, right, the data sitting in X2 will be available here, then the data sitting in X3 will be available at this point, okay, after TRF read delay. Now, most importantly, you will notice that if you take this particular block here, the MUX block, okay, so the IMM source is going to come, with some delay, and then the with some delay, we'll come to this when we do the I type of instruction, but it's going to take some time for it to go through that whole immediate process, I mean the extending process and all that. But X3 is going to be available after TRF read at this particular, at the input of that multiplexer, right? Now if I look at the timing here, X3 is available after TRF read and this one is available after T decode. Remember that, because those outputs are all coming from the control unit, right? And therefore, if you look at it, source A, right, which is one of the inputs to the ALU, is available exactly after TRF read from the time the instruction is ready, has been read out from the instruction memory, whereas source B is going to be available after TRF read and T decode, right? So therefore, what I am actually marking out here in red is actually the arrival time. It's not just the delay. So what I'll do is, maybe I'll use a different color to mark the arrival time. So this is the arrival time of the signal. So from the clock, if you look at it, we are talking of T PCQPC, T mem, and then T decode, right? On the other hand, so source A, arrival time, okay, let me write that. Arrival time with the clock edge being reference 0, right, at source A. What is it? It is basically T PCQPC plus T mem, okay, plus at source A, right? So source A has really no control unit influence on the register readout, okay, source 1, okay, the source, that is the A1 address, right, and therefore that is just going to come out after TRF read straight. On the other hand, if you look at source, right, so source B is the output of the multiplexer, right? So what happens is, if I look at the input, okay, let me call these inputs as I1 and I2, okay, so I will look at the arrival time at I1. What is the arrival time at I1? It is basically just the path that is identical to source A. So actually this is exactly the same as this arrival time. I2 on the other hand is going through, you know, some decoder, it has to come through thing, there is an extension block. So there is some other time at I2, the arrival time is different. Okay, it is different because of, you know, it has to go through the extender block for immediate data processing and all that, which we will do in the I-type instruction analysis, right? Essentially now, therefore, if you look at ALU source, right, the ALU source signal, the other input to the multiplexer is what? Is the ALU source. Okay, and I will say here it is, I will use again, I'll use this, it does not matter. Why? Because ALU source is 0 and therefore it's only that path that is actually going to really, you know, that's the delay that we need to worry about in this case. So ALU source on the other hand is available after PCQ of PC plus TMEM plus T decode. Okay. Now if you look at the arrival time, so what is the arrival time at the output of the mux? It is basically the maximum arrival time at all the inputs plus the delay through the mux. Okay. So therefore the arrival time at source B now, what is that? At source B, it is going to be the maximum of TPCQ PC, no, again wrong color, so max of TPCQ PC plus TMEM plus TRF read, comma TPCQ PC plus TMEM, right, plus T decode, the maximum of that plus the arrival time, the delay through the mux. Okay, and that's why what you see here is ultimately the arrival time at the output of the mux source B is going to be TPCQPC plus TMEM plus maximum of TRF read and T decode. We saw that the RF read was significantly higher in terms of its delay number and therefore that is going to dominate, and that's why we are not going to worry about this T decode number at this point. So this is T mux. Okay, and then now if you look at the ALU again, right, the ALU again has multiple inputs, source A, source B and the control signal. Again the control signal is, you know, from the time the instruction is available, it is ready at after T decode, whereas source A comes after TRF read, source B comes after TRF read plus T mux. Okay, so which one is the most dominant path? It is obviously the RF read plus the mux path, and then it has to go through the ALU for this TALU, right? Now the write enable is, you know, 0 because it's write enable for the data memory, because there is no data memory operation here, it's an R type instruction, and therefore what you're going to do is you are effectively going to go through which path? I'll write that in green. So you will get this, you will go through the bypass path. Okay, again this mux has many inputs. Okay, one, the input is, of course, result source is going to be 0 0 because it's an R type instruction, right, and therefore you are going to worry only about this path. This also will be a T mux. Okay, and ultimately you are going to come back through this path and come back to the right data port of your register file. Remember, that has to be set up TRF setup before the next clock edge. Only then the data will get written in the subsequent clock edge appropriately, right? So therefore, if you look at this whole thing, right, you start from here, you're going through this thing. I would say going through A2, come here, go through this, come all the way. You start from the program counter, trace that path, come back, and therefore the delay that is incurred for a register file, okay, TC min, the minimum clock required for our type of instruction, let's put that down, is what? Is TPC QPC plus TMEM, okay, plus TRF read plus TMUX plus TALU plus another TMUX, and eventually you will have to set up before the register file setup time, okay. So the minimum clock period required in order to handle just R type, let's say I did not have any other kind of instruction, then I would need this minimum clock period for me to handle this particular operation.